solution to ETFS and an algorithm how to find it. Thirdly, I will prove the complexity of our ETFS algorithm and prove conditional lower bounds on the complexity of any algorithm solving ETFS. And I will end with a short summary of the talk. So let's start with the introduction. So we have an alphabet sigma, which is finite. Then we have a string W over sigma. And then we denote substrings like this. And a k-mer or pattern is a substring of length k. In general, patterns can have arbitrary length, but for this talk, they will always have a fixed length k. So data sanitization is an area in data mining, which has been around for about 20 years. And the issue is that data collectors, they collect a lot of data, and they often send it to third parties for analysis. However, this is often not possible due to privacy reasons. And what data sanitization does is that it modifies this data such that it satisfies certain privacy constraints while maintaining certain utility properties from the original data. We work on string sanitization, where the data is basically a string. And this was introduced in the 2019 paper by Bernardini et al. And so we have a string W, which may represent all kinds of data like location history, search queries, a DNA sequence, etc. And such a string is used for analysis. However, sharing this string may expose patterns modeling confidential knowledge. We call these patterns sensitive. So very simple example, let W be our string, then maybe the patterns BAAA, AAAA, and BBAA are sensitive, and we underline them in red. And the goal of string sanitization is to conceal these sensitive patterns while maintaining the data utility of the string. Okay, now let's look at the other part of our title, added distance. So the added distance between two strings is the number of insertions, deletions, and substitutions to transform one string S into string T. In general, these operations can have certain weights, but we assume that insertion, deletion, and substitution all have weight 1, and matches have weight 0. So in this example, if we align the strings like this, then we have 1 insertion, 1 deletion, 2 substitutions, so that is an added distance of 4. The classical algorithm to compute the added distance between two strings is Levenshtein's algorithm. And here we compute a dynamic programming table where the entry Eij represents the added distance between the length I prefix of the first string and the length j prefix of the second string. And we can compute all the entries using the recursive formulas shown below. And then in blue, we have a path corresponding to the optimal alignment between the two strings. So we use the model, the combinatorial string dissemination model, which was introduced in the same paper by Bernardini et al. And it says that given some constraints and properties, we want to determine the added operations that we have to apply to the string W to satisfy these properties subject to the constraints. And in our setting, that will be we are given a string W and a length and a set of length k sensitive patterns. And now we want to construct a new string X such that the following holds. So no length k sensitive patterns occur in X, such that we don't share confidential knowledge. Then we want the order of the length k non-sensitive patterns to be preserved in X. So non-sensitive patterns are all patterns that are not sensitive. And that way there's no utility loss for tasks based on the sequentiality of these non-sensitive patterns. And thirdly, we want that the frequency of these length k non-sensitive patterns is preserved as well. So we don't have any utility loss for tasks based on frequency. Now the ETFS problem wants to construct a string XED, which satisfies these three properties. And in addition, over all strings that satisfy those three properties, we want a string that is closest to W in terms of edit distance, so that there is as little utility loss as possible for tasks based on edit distance. So let's look at an example. We have an alphabet of size 2, a string W. Over these alphabets, we choose the pattern length to be 3, and we have the following set of sensitive patterns. So in this example, I have underlined all the sensitive patterns in red, and then the remaining non-sensitive patterns, I have overlined them in blue. So as you can see, this new string X, it contains the patterns BAB, ABB, BBB, and BAB in the same order and with the same frequency as W. Note that we have to use a separating character here between the last two patterns, because if we would leave that out, then we would create extra non-sensitive patterns like BBB, and we want that all the patterns over the non-sensitive patterns over sigma are preserved and that we don't introduce any new ones. So we need a separating character here. Well, the solution is not unique. For example, we can have a solution like this, XED, and as you can see, it contains exactly the same non-sensitive patterns of length 3, so BAB, ABB, BBB, and BAB. But now we have used some extra separators, and note that we can even have small strings in between, as long as their length is shorter than k, because we don't want to introduce any new length k patterns. So the edit distance between X and W is 6, while the edit distance between XED and W is 4. And it turns out that the minimum edit distance between such string and W is 4, so XED would be a valid output of our ETFS algorithm. Now the theorem this paper is about is that we have an algorithm, ETFS dp, which solves ETFS in k n squared time. So, what are the possibilities for such a string XED? So if you have two pairs of consecutive non-sensitive patterns, then there are two possibilities. If they overlap by k-1 patterns, then we can merge them. And in general, we can always interleave them with a carefully selected string over sigma and hash. So in this case, we can see that we interleave them with a string, and then even though we could have merged them, then here between the second and third pattern, they overlap by 2 letters, so we can merge them. And then for the third and fourth pattern, we cannot merge them because the third pattern ends in BB and the fourth pattern starts with BA. So therefore we have to interleave it with a string and we choose a single hash. So our algorithm, ETFS dp, is inspired by Levenstein's algorithm. So we have a similar dynamic programming matrix. And we have string W at the top. So for example, the column with a 5 corresponds to a length 5 prefix of W, and the column with 0 represents a length 0 prefix of W, so that would be the empty string. However, we don't know what the other string will be. We just know that it has to consist of these non-sensitive patterns. So therefore, we just put the non-sensitive patterns on the left-hand side, interleaved with a small box, and that small box can represent any string to be interleaved between the non-sensitive patterns. And then we have a slightly different one at the beginning of the string and the end of the string, because we can also put a gadget there, but that's a technicality. Okay, so what happens in the first column? Here we want to find the minimal edit distance between these non-sensitive patterns and the empty strings. So actually we just want the minimum length string XED, and well, at every symbol the length increases by 1. However, once we get to the second pattern, then we can merge the second pattern with the first pattern, and then those patterns merged will only have length 4 instead of length 3 plus 1 for separator plus length 3. So instead of a 7, we get a 4 here. And then it goes up again, 5, 6, 7. Then we can merge again. So we take 4 plus 1 is 5, 6, 7, 8. Now we can't merge the last two patterns, so we get 9 and then 10. Okay, so most rows that are not the last, that have letters in them, but they are not the last of a non-sensitive pattern, so we cannot merge. They work exactly the same as in Levenshtein's algorithm. So we get exactly the same recursive formula. However, in these merge rows, it is possible to merge. So as you can see here, we have a pattern BBBB, and actually we can also see it as just ABB plus an extra letter. So if we are here, then we can, instead of jumping to the previous letter, we can jump to that letter in the previous pattern. And that results in these two extra rows in the recursive formula. Note that this is only possible if there's this suffix-prefix overlap of length k-1. So during the pre-processing step, we have to check where that's the case, and as we have seen before, it can be done the first in the beginning, but here these last two patterns, BBB and BAB, they cannot be merged. So here ML would be 0 for cannot merge, and then we only get the first 3 formulas, and we are again just in Levenshtein's algorithm. Then the gadget rows, they are a bit tricky. So as you can see, we have here gadgets, and so actually we can get k in this case 3 steps further for a cost of 1 hash, because between these two hashes we can just copy exactly the same letters for cost 0, and then we have 1 for this substitution. So this part has cost 1, and we got 3 steps further in W. So we can make a jump of length 3 here. In general, we can make jumps of length 1 to k, and that results in these extra options of jumps of length up to k. So we have order k entries to compare. Okay, so what does this mean for the running time? So we have at most k and ordinary rows, because we have at most n patterns of n non-sensitive patterns of length k, and these rows have length n plus 1, and we have to do 3 comparisons, so that's O of k n squared. Then for the merge rows, well, we have only 1 per pattern, so that's n times n is n squared. We still have a constant number of comparisons. For the gadget rows, we suddenly have order of k comparisons, but there are only n of them, so we're fine too. And then there's the pre-processing, like allocating matrix, that also takes O of k n squared. So the total running time of this algorithm is O of k n squared. Then the conditional lower bound. So we prove that ETFS cannot be computed in strongly subquadratic time, assuming the strongly exponential time hypothesis. And the main theorem we use to prove this is the theorem by Brinkmann and Kuhnemann. Let P and Q be two arbitrary strings of length n, and suppose the strongly exponential time hypothesis is true, and the added distance cost parameters satisfy some reasonable assumptions. So this is the general case where added distance, where insertion, deletion, match, and substitution can have arbitrary costs. Then we cannot compute the added distance between P and Q in strongly subquadratic time. Okay, so our idea is that given two strings P and Q of length n over the alphabet sigma, we construct a new string, very complicated string U, such that we can actually calculate the added distance between P and Q in strongly subquadratic time, given the ETFS output of U, and well, because we cannot find the added distance between P and Q in strongly subquadratic time, we cannot find the output of ETFS in strongly subquadratic time either. So, so yeah, basically this string consists of 4 parts. Here we have a very repetitive string. Then here we have a string that contains all the letters of the first string P. Then we have a very similar repetitive string. And then finally we have a string that looks a bit like F2, but now with the letters of Q. So we define the non-sensitive patterns to be A, A, B, A, A. So we take these are patterns from F1. And also C1D and then a letter of P, C2, C3. We take these from F2. And we say that all other patterns in U are sensitive. So almost all patterns are sensitive. Now we can prove that it's always optimal to align the first x plus 1 AB patterns with F1, then use a very long gadget to align with F2. So a gadget that's just something that's interleaved between the non-sensitive patterns. So here our pattern length is 5. So we have at most 4 letters, and then we need this separating hash in order to not to introduce any new patterns of length 5. Now then we use the other XAB patterns to align with F3. And then the C patterns have to be aligned with F4 in this specific way. So either we have a part of F4 aligned with a gadget part, so 1 hash and 4 letters, or we have a C pattern, which is just inserted and not aligned with anything, or we have a part of F4 aligned with a C pattern, and then there are 2 possibilities: either the letter in P and the letter in Q don't match, or they match. And note that this actually corresponds to an alignment of P and Q with the following costs. So this is like insertion into Q, and it has costs 1. This is like deletion from P, and it has cost 6. This is like a substitution, and it has cost 1, 2, 3. And this is like a match, and it has cost 1, 2. Now, these specific cost parameters actually satisfy the conditions by Brinkmann and Kuhnemann. So we cannot compute the added distance of this part of U in strongly subquadratic time. So we cannot calculate the added distance between U and XED in strongly subquadratic time. Now, if you've paid attention, then you know that the ETFS problem doesn't actually require us to calculate the added distance between U and XED, but wants us to find XED. But with some tricks and running ETFS twice instead of once, we can actually use ETFS to find the exact alignment and then prove that we cannot find the string XED in strongly subquadratic time either. Okay, so to summarize, string sanitization removes sensitive data from strings while maximizing utility. And the ETFS removes sensitive patterns while preserving the total order and frequency of the non-sensitive patterns and minimizing the added distance of the original string. ETFS can be solved in O of k(n) squared time using the ETFS DP algorithm, and no ETFS algorithm runs in strongly subquadratic time unless the strongly exponential time hypothesis is false. So that was my talk. Are there any questions?